This is going to be largely another review lecture on wave-particle duality. So this is some amount of review, but also some amount of new stuff. So in Chem 109, and I think some of your other physics classes, you talked about wave-particle duality. So I'm going to talk about that and maybe go into a little bit more detail that perhaps you haven't. So the first thing that I want to talk about is the wave theory of light. And so, of course, wave-particle duality, meaning light can behave as a wave, but also as a particle. So Young's double slit experiment is kind of the famous experiment showing how light acts as a wave. And the experiment goes something like this. So we have this double slit. I'll see if I can't annotate this. So like here is an opening, and here is an opening. So there's our double slit, right? And so, of course, there's a source of photons up here, a light source. And that light source, as it comes through, it's broad. And in one experiment, only the right slit is open. And when that happens, another beam of light converges out. And what you would observe on a screen here is just a continuous band of light. So there's no features, it's just a continuous band. Okay? So then in the experiment, we close the right slit and open the left slit. And the same thing is observed, it's just shifted over to the left a little bit. Okay? But now something different happens when both slits are open. This is very fascinating. So when both slits are open, you can see we get two beams of light. And then what was observed is down here below. Okay, oops, I used a black marker there. That doesn't show up. So what was observed is down here. And you notice now there's no longer this continuous band of light. There's features. Okay? So it has this kind of what I'll call a striped pattern, right? There's some regions where there's no light, and there's some regions where you do see some light, okay? So according to particle theory, when both slits are open, it should give us just the same observation as when the two individual slits were open. So it's kind of like if you imagine, instead of this being light, maybe it's like water or something, right? You open up these two slits and like the floodgates open, and according to particle theory, you should just see like this continuous band. Well, according to wave theory, you should see a structured or a banded pattern, okay? And that's exactly what was observed. So this experiment confirmed that light acts as a wave. And the reason why you're getting this kind of structured, patterned, banded observation is because of the interference pattern of the waves. And so that's what you're kind of seeing here. So interference, okay? So as the wave front propagates through, okay, the double slits, there are going to be regions of constructive interference and regions of destructive interference that owe to this banded structure, okay? So where you see regions of light, okay, like perhaps here and here and here and so on, those are regions of constructive interference. But now where you see regions where there's no light at all, those are regions of destructive interference. So to review that, so we recall, when we add waves together, and mathematically this is true, but also physically this is true, right? If we imagine two parallel beams of light in what we would call in phase, so this yellow box right here, we would call that light, those two beams, they are in phase with each other. So in other words, the peaks line up and the troughs line up. okay? And we usually indicate the phase by the degree. So for example, now if we change the phase of these two lights by 90 degrees, okay? So, and the reason for using that degrees, right, is we're really kind of thinking about the conversion of that degrees into radians, okay? So, but now if we shift the phase of these things, they are now out of phase, okay? And so now the troughs and the peaks line up, and the peaks and the troughs line up. And that owes to pure destructive interference. So again, when we have two beams of light that are in phase with each other, we get increased amplitude. So you notice here this is saying, if the amplitude is represented by the letter A, and both are A and A, then our new constructive interference will be twice the amplitude. And what that means is the light will appear brighter, okay? It will be amplified. And now, in the case of these two beams of light being perfectly out of phase, we will see no light at all, owing to dark spots, okay? So we are going to be talking about interference all semester, okay? It is a very important phenomenon, not only in light, but also with electrons, okay? So this is a start of the basics, right? Pure constructive or pure destructive. What we're going to see this semester is a lot of examples of things in between this pure in phase or pure out of phase, which will give us a complicated interference pattern. Okay? So moving on, let's just briefly talk about light as a particle. So of course, if we repeated this same experiment, we could also describe the double slit experiment if we had these narrow openings, and this thing represents our screen, okay? And of course, this is assuming that when the particles funnel through here, they're maintaining like only a certain width through this beam, okay? And so we would see a bunch of different photons hitting the screen, and that's what we would view, okay? Now, of course, if the light beam coming out were divergent, if it was expanding like this, okay, like in Young's double slit experiment, then we would just see, I'm going to try to represent particles of light. We would see these photons all over the screen, okay? And so it would look very much like this picture right here, the particle theory picture, okay? And so notice that that's very different than this interference pattern, right? Whether we had what we call a collimated beam, so I'll spell that. A collimated beam, which would be a very narrow beam of light, or a divergent beam, something that's expanding out, okay? We would just see a continuous band of light. We wouldn't see this banded structure owing to an interference pattern, okay? As it turns out, laser light shows take advantage of the particle theory of light. Little did you know. And so the way that this works is, in these laser light shows, you typically have some type of smoke particles in the air, okay? So and I'll represent those by, showing all these little particles. We would call these aerosol, okay, or smoke, if you like. And as a collimated beam comes through, so I'm going to represent that by just drawing a narrow line. Maybe we've got a red laser. So this collimated beam will come through, and as soon as it strikes one of those smoke particles, it's going to scatter in all directions, okay? And so what you see, because it's scattering in all directions, it doesn't look like this continuous, sunlight, like this big divergent lamp. Rather, because there are thousands of observers at thousands of different angles, Okay, so I'll draw that by saying like, you know, here's an eyeball, here's an observer, right? Here's an observer. What we see from these beams scattering all around as they collide with these smoke particles is we just see the collimated beam. Okay? If we didn't have any smoke particles in the air, we would not see this collimated beam. Rather, what we would see, much like a laser pointer, I could demonstrate this to you easily in the classroom, right? If I pointed a laser pointer, right, imagine I'm firing one across the room. If there's no, particles or smoke or aerosol in the air to scatter that beam, I wouldn't see the actual beam. I would just see where the laser is reflecting off of the wall, right? You've all experienced this at a presentation when someone is shooting their laser pointer at a screen, okay? But if there are things in the air which can scatter that light in all different directions, you will see the collimated beam, okay? And that's well described by the particle theory of light. So these are just two very simple examples. All semester we're going to be dealing with wave-particle duality. And it's not just light that is suspect to this. Electrons, too, are suspect to wave-particle duality.